Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about locomotives. So let's dive deep into it. So before we understand locomotive, we have to understand what kind of power scale we are talking about. Well, in simplest term, we are talking about a lot of power, like GG amounts of power, like seriously large amounts of power. And generally we have two categories. First category is goods train, the backbone of society. It generally tries to get long and as heavy as possible. Like in case of India, we generally have a very good broad gauge network, but to make sure that freight becomes far more lucrative on rails rather than trucks, we created a whole new network known as dedicated freight corridor. The only different gauge is same. The only difference is the ton allowed per axle is much higher. So we can absorb much heavier loads. So goods train, heavy, awesome. Passenger train, what is the requirement of passenger? Speed. It has to be as fast as possible. That's the only aim about passenger trains. If you're building a passenger train, what's your target? Make it as fast as possible. You're making a goods train, make it as long as possible, make it as heavy as possible. Now, whenever you're talking about modern locomotives, generally they do not even start less than 3000 horsepower in mainline. Of course, you could have stunting locomotives that are working in small jobs and all that. That's a different thing. But when you're talking about locomotive, generally you start at 3000. It goes only up from there. What is 3000 horsepower? It's a very big number. So think in this way, 2.2 megawatt. That's a lot. What does that mean? That simply means a locomotive like this, if you take the alternator unit that is creating the main electrical energy, you can power something that is 2 megawatt load. So serious horsepower, not some joke, serious. Now it may look like, isn't that very inefficient? Well, consider how much ton of payload it moves. Yeah, it's free. So that's why we make it so powerful. Then how big that can go? This is one. India has two locomotive. There is WAG 11 and there is WAG 12 right now, which is the India's most powerful one. That goes up to 12,000 horsepower. And that puppy is 8.9 megawatt. One engine. Unfortunately, it's a dual cabin design, so it has dual cabin because again, traction. It does not make sense to have 12,000 horsepower in one small unit. It like wheels will slip, and your axle loading may exceed the threshold. So it had to be spread out. 12,000 horsepower. There's only one design, but it has like 3 to 4 cabs. One Russian design that is, if I'm not mistaken, goes to 7,000 horsepower. What is the highest that I have seen? Well, highest I've seen is 17 megawatts plus. But that is high speed train. Now be mindful, when you're talking about this is a multiple unit, meaning it does not have one locomotive. It does have driver cabs, both side, but it's not locomotive. Locomotives in every axle. And this puppy, when they built it, Japanese people, when they built it, this consumes more power compared to TGV. Now, like, why? Well, speed is more or less the same. Heck, actually, I think TGV does travel a bit faster. But what they built with this is like a densely populated area, basically like India. So the core logic was this puppy should move people, like seriously large amount of people should be able to go in and go out. So achieve that, they used non-Jacob bogie. Basically, Jacob bogies are, you have coaches. Between the coaches, when you are joining the coaches, you're going to put bogie here. Benefit, you reduce the numbers of grand total bogies. And speed becomes more efficient. Everything is awesome, but it does reduce your tonnage, how much ton you can haul on it. This puppy, because it needs to haul a lot of people, it was designed in such a way which each coach had 2 bogies. So number of axles became exponentially higher. Benefit, super fast acceleration and seriously large amount of capacity. That's why India is working with Japan right now to develop this technology, specifically tailor-made for Indian system. Because again, if we try Italian system or European system, it will not work for our density. And this are the transformer, basically the heart of electrical locomotives. And these puppies, small puppies that you are seeing, yeah, they rate upwards of 6 megawatt. Up to, not all of them are that much. Generally 4 to 5 megawatt is common, but it can go to that level. So serious power we are talking about. And these lines are generally 25 kV. Only that Russian one is weird, where it's like 3000 volt DC. I'm like, why the heck they're still using DC? So distribution. You have the power, how the heck are you going to distribute it? Well, the most common system, the simplest thing you can think of is locomotive in the front. If you ask a child to draw a train, that's what they draw. There's an engine and it's pulling wagons. That's it. It's super simple. The benefit, it's simple, meaning how do you operate it? How do you maintain it? Everything becomes simple. It's easy. It's low cost, meaning if you are delivering freight, you do not have the luxury of charging whatever the hell you want to charge. People are like, hey, bring it slowly, but bring it cost effectively. That's why we use shipping containers. So in those sort of scenario, people are like, okay, let's make it cost effective. Awesome for that. Then we have multiple locomotives. For example, this is a railway locomotive experiment that was done with India, where they put 2 locomotives and it was in push-pull configuration. So this is one way you can increase the acceleration and deceleration of a locomotive. And this had the passengers experience was like, it was quick. Like train was like, it's a bit weird. Whenever you press accelerator in a basically car, you get pushed behind the seat. It rarely happens in a locomotive or a train basically. Passengers rarely feel like, whoa, unless you are in Japan. Here, this train actually gave Indians that example. It was like, whoa, 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 whoa. Train started to go that far. Then you have something in between. Now, this sort of things become compulsory if you really want to make a very long train, because the weak link in this scenario is not the locomotive, nor its horsepower, nor even the tonnage, is the linkage. Linkage is like, I can't hold it. So to protect against that, you have to put something in center. So if you want a lot of oomph and super long load, as in like kilometer plus, in those sort of scenario, we may prefer to put something in between. Then we have multiple units. Now, so far I was only talking about locomotive. How do you place the locomotive? What if you want to digest the locomotive, like India's current medium speed train? So in this scenario, every other axle or every other coach, depending on the design is not final. As in like it's still working, but they are fine tuning it depending on the feedback. So that would be powered. Meaning this front area is not locomotive. It does have driver's cab, it does have all the control electronics, but it's not locomotive. The locomotive is in the bogie, and multiple bogies have that benefit: super fast acceleration and super fast deceleration, and it's also more energy efficient. Yes, it does increase the cost exponentially, exactly like TGB or other systems, but it is efficient also. That's one saving grace of this sort of design, because it's distributing energy over a large area. The grip factor helps it, the traction helps it, and it can actually climb up steep gradients much more efficiently compared to a locomotive that is just like hauling ass. So this is the distribution aspect. How do you distribute the power? Generally for goods, people still prefer locomotive in the front, but if goods train starts to get too long, people may have to put something in back, or may put something in the back also for pushing. If you want basically a lot of speed for acceleration specifically for passenger, you may want to use digested design or multiple unit. Now we come to the heart of the issue: electricals. If you go to 200 countries on the planet Earth, that there are grand total, almost all nations can build everything about locomotive, modern locomotive, except this puppy. Like everything in other than that is just copper and steel and aluminum and nothing fancy, nothing fancy. It's just like it can be built anywhere on the planet. Then why can't we build it? Heck, even in Russian designs, you can look into it. They will tell you, oh, the motor driver and motor, the set is from Siemens. Look at somewhere else, it's like, okay, it's from ABB. This is the hard part. The motor driver, basically, how do you take the energy and drive the motors with it? That's very, very idiotically difficult. Back in the days, we used to use DC motors. Now, problem with DC motors is like it used to have brushes. Now, brushes, when you are talking about in those sort of horsepower, like each motor could be like 500 horsepower, brushes are carrying significant amount of energy. There was a very serious fire risk. On top of that, that's motor, that's like 500 horsepower. What about the dynamo that was generating that DC power? So that was a very serious risk. Early days of diesel locomotives used to catch fire a lot, and brushes were the primary reason, specifically in dynamo, because dynamo had the concentrated energy. So we upgraded. Thankfully, silicon was developed. We developed silicon bridge rectifiers. Bridge rectifiers were dumb device. It does not need a controlling mechanism. We just replaced the dynamo with alternator. Alternator started to create AC. AC was made into DC. DC was used to drive the motors. Everything is fine and dandy, but it's very inefficient. Not very as in like very, very inefficient. It's just like if we could do better. Still that point, almost every nation should be able to build it. But the moment we introduced the technology of IGBT, before this thyristors were tried, but it was not that exponentially better from DC. So people were like, is it really, because again, thyristors were expensive. IGBT is again even more expensive, but they actually give you enough benefit. People are like, okay, I can see it. So IGBT inverters basically taking DC, making it into AC. That's how we drive modern locomotives as of now. Now, tech defines your efficiency limit, meaning how much energy you're taking from pantograph and how much energy is going into the motor, actually like pulling the train. That efficiency is limited by topology. What topology are you using? If you're using thyristor, do not expect too much. If you're using IGBT, again, in that IGBT, there is a categories like how efficient the design is, what sort of systems you are using, how many phase corrections are there, like a lot of complex math. In those sort of scenario, you will define like, is only going to be like 75% efficient, 84% efficient, 92% efficient. You're never going to exceed what your technological limit is. So tech defines that, and only few nations on the planet can actually build it. Like, this is a very old design. Be mindful when I'm saying old, you have to understand locomotives generally do not age like mobile phones. They age like fine wine. So you can easily have a locomotive that actually has this design right now. So you have an electric pantograph. Be mindful, if you want to think about diesel, just yeet this part, put a alternator there. So you have a pantograph, goes into transformer that I saw in the first slide, and then you take the energy. You take the energy, it goes to AC to DC converter. It becomes DC. DC goes to DC link. DC link generally introduces some filtering component, for example, inductors and capacitors to filter that puppy out. All of that data is being monitored by converter inverter controller. DC link feeds into pulse width modulation inverters. This inverter feeds the induction motor. Induction motor drives that. Now, pulse width modulation is the very basic, very early days of IGBTs. Like, does this work? Absolutely. Heck, you may have a system that is using this, but it's very early days, like as in like late 80s, so to say. That's pulse width modulation. This is how we started. Then in late 90s, again, be mindful, the years are offset. Every country will tell you like, oh, we use this and that, then it did not work. Then, because be mindful, designing this thing is easy. Validating it in a railway environment where it keeps working year in, at least 10 years, yeah, that's the difficult part. So this is another topology where you have a pantograph, a giant transformer, and you have four loops that are pulling out of it. Then it goes into that synchronous link converter unit, and that dumps into the DC link. That DC link dumps into VSI link, which is basically a more efficient version of PWM, and that's how you drive the motors. And there is this another version which is even more complex, and my brain quit at that point. So you have to, this is the part which is hard. If you want to design a locomotive, almost everything else you can literally collect the data for it. Like, why did you have this geometry? There is data on that. Everything is known, everything is understood. We know that. Like, it's open knowledge. The moment you want to touch electronics, it's like, good luck, sir. Good luck. Because be mindful, designing it, building it, that's the easy part. Making sure this complexity survives a day-to-day use of a railway, yeah, that's the brutal part. Be mindful, these things cannot just go down. Like, when this system was designed, it's designed in such a way that half of the units can go down and you will still have 3 powered axles. And even in that 3 powered axle system, one motor can go down and the system will still survive more or less. That's the whole point. These things have to be robust and reliable. So that's why ABB, Siemens, Hitachi, these companies are the leaders on that. Almost nobody else has this caliber of technology. Because normal motor driver, how powerful that is, 100 kilowatt maximum. These puppies start at 1 megawatt starting range. Then we come to the motor side of it. Now, motor is very simple because we started with DC, magnetless. Early days people did try to put magnets, but then they realized tracks, stuff, catching stuff. So magnet was removed, brushless. Basically a universal motor design was chosen, like some variant of that. If you want to look at what exactly it looks like, it's very hard to find nowadays, the photos. But topology wise, it would be almost similar to universal motor. If you have old washing machine, they have this motor, so you can physically see it. Nowadays, we have moved away from universal motor to AC induction motor. Why? Brushes. Brushes were a very serious hazard in dynamo era. We removed it. Now we are like, okay, if we have the control electronics, now we can achieve efficiency, meaning the amount of fuel in tons that you are consuming goes down. So for that reason, people are like, let's use the efficiency. So AC induction motor is a bit more efficient. And in some designs, you can even have synchronous motor. And some designs, even less than that, you can even have magnets to give you extreme efficiency. So these are generally the options that are available. Now, be mindful, when we're talking about these sort of motor, it's huge. They can consume, each motor can consume upwards of 1 megawatt as surge. So consequence of that is, they require cooling, because even if a motor is 90% efficient, that means 10% would be wasted. Think about 10% of 1 megawatt. Yeah, that will fry this motor instantaneously. So for that reason, every locomotive motor that is powerful enough generally requires forced air cooling and cooling seriously, like, and this also helps to elongate the life of this puppy because it's always positively pressurized. So whenever you look at the locomotive, so you will see the axle will have a sleeve will have the gear will be bound to the basically motor, and that motor will have a shock that is going up like this sock. Like, why the heck there is a silicon sock there? That sock is the air duct. Now there is a giant filter box and giant blower that is blowing, sucking air through the filter box, dumping into the motor. So motor is always positive air pressure, so it's always dumping dust out. So even if you're going through desert, dust will not go inside it if things are working properly. If things are broken, God help you, but generally that's how it's designed that way. And filters generally have sensors, so if filter starts to either malfunction, as in like let dirty air through, it will trigger an alarm. If it gets clogged up, it will trigger an alarm. So that's how we do it. Cooling, like the motors that are used just to cool these motors are so huge, it can drive your like normal day-to-day household loads. That's how powerful cooling requirement is. It's brutal. It's brutal. And if you ever wondered, like India have two series of locomotive. We have WAP and we have WAG. WAP is WAP, wide gauge. A is for AC traction. We used to have DC traction in early days, 1500 volts. Generally, early Mumbai area used to have that. That was removed now. For AC traction, 25 kV. So we have wide gauge, AC traction, and P is for passenger. So WAP is passenger locomotive. Generally this will be the same, only the gears that are used would be changed. So basically the gear ratio would be designed more for speed rather than torque, and in for goods train, WAG, goods train, it would be designed in such a way that it has more oomph, more torque. Speed would be limited, as in like the top speed will not barely cross 80 kmph, but it will be able to haul load. So this is the motor side of things. Then we come to the brakes. So far we are just going places. Okay, we are doing this and that, all that is awesome. But here's how do you stop it? Well, here's the problem. The very thing that makes railways so attractive, so desirable from an environmental point of view, from an economics point of view, is that metal on metal is very low rolling resistance. Meaning, if you take a wheel and you inflate it with as much air as you can do that, drive it on the best road you can find, autobahn, let's just say, and still would be like horrible. It will be horrible. You do the same thing, metal on metal wheel, the same amount of horsepower going in, the amount of motion, like the amount of distance you can cover would be exponentially higher because of very low rolling resistance. Outcome, efficiency. Problem, efficiency. What does that mean? That simply means if you apply brakes, if you go like Tokyo Drift on it, it's like, hey, apply brakes, wheel will stop and it will just keep sliding on the track because there is not enough friction there. And it, of course, it will heat it up and destroy it. And if railway officers find you are the reason why you are doing Tokyo Drift, they will fire missile up your ass. So that's the problem. Wheels can stop too early, meaning if you have air brakes and you just like bam it, just ram it into the wheels, yeah, you're gonna do locking mechanism. Now be mindful, modern locomotives do have anti-lock braking system. Yes, it's almost the same ABS technology that is used in our normal day-to-day cars. So wheel can stop too early. That's the biggest. It will have flat stop, flat spots if that happens. So it's a very no-go scenario. So how do you stop it? Now, this is the primary reason why every axle must have brakes. Like it may have power, may not have power. That's not an issue, but it must have brakes. And that's the primary reason why we have brake lines and all that. So brake lines, or each basically bogie is designed to work in such a way that even if bogie attached to it, as in like one coach, two bogies, one bogie's brake unit fails, it still should be able to handle at maximum loading all the speed that is rated to. So let's say it's rated to 150 kmph. The basically brake unit on one bogie should be able to handle that. Now here's the deal, that's not enough redundancy, so locomotives takes the most of the loading. Now how the heck locomotive is gonna do that? They will also have the same issue. It's like wheel, if they apply too much, the wheel will lock up. If they do too slowly, it won't actually slow down the train because of the mass involved. So we introduce dynamic or regenerative braking. Now this is a very ancient technology. It's like you will be shocked how early we figured it out. In DC it's kind of easy. So dynamic braking allows you to basically leech off the energy. Where is that energy coming from? That is the acceleration energy. The energy you invested in order to accelerate your train, you are just saying, hey, can you please return that? Now what the heck you do with almost few megawatts of impulse energy that you're gonna get? You're gonna dump it into braking resistors. Like this is night time, so you can see the resistors actually glowing. And some people are saying it's not supposed to be glowing. That means the cooling fan has failed, because again, you're dumping megawatts of power for short burst into those resistors. The resistors do glow, like especially in high humidity environment, you can see like heat wave coming out of that. And they have a fan, giant powerful fan connected, that will only work if the braking grids are on. And again, it also leaches the energy off from the motors. That's the easiest way to slow down the train. For example, if you want to apply a brake on a very heavy train that is traveling at 100 kmph, you can apply brake once. So that's good. What if you are traveling at 150 kmph to 0 kmph? Yeah, emergency brake and bye-bye train. So what the heck we do? We apply dynamic braking, meaning now you accelerate like without any worry, decelerate it from let's say 150 kmph to 50 kmph. Be mindful, regenerative braking does not allow you to go to 0. It will only slow you down, but it will never allow you to go to dead stop. You leech off majority of the energy, then you apply basically normal braking. Now, would normal braking be able to handle a train if, let's say, dynamic grid fails? Yes, but only once. It will require serious maintenance after that, and that's assuming if train was like within tolerance, everything was fine. But worst case scenario, it has caused issue where there is like very serious rule: if dynamic brake is not working, reduce the load on your train. And if you ever in a train, passenger train, whose dynamic braking system failed, you will know train will randomly start to make way too much noise every time it's stopping. And you will really feel, train should be traveling faster. It's not traveling as fast. Like driver would be like, yeah, I don't trust this train anymore. Now, of course, I'm exaggerating, but it's same thing. And nowadays, because of the better electronics, we have the ability to redump the energy, meaning the energy that is instead of wasting as a resistive grid, you can dump it into the overhead wire. You can consume it for auxiliary unit, or you can just put it into batteries. Yes, trains have generally very big battery banks. So a lot of things can be done. Be mindful, that's the only reason we can make trains this long. If you remove resistive braking, yeah, trains maintenance cost will go lol. Brake shoe stocks will go up. So this is the brake side of things. So this was my presentation on basic level of Locomotive. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show my extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.